So I've seen a lot of people struggle with creating abstractions or wrappers for their database clients in effect. So let me show you my adapter for Drizzle, and maybe you can learn a thing or two on how to connect to the database, how to model the errors, and well, how to access the runtime and use that for fallback style functions, which is always tedious to work with in effect. So there are a couple of issues with this vanilla implementation. First and foremost, the pool, establishing a connection with your database. What if that fails? Could be a transient error, could be that your database is offline, or maybe you established a connection, the server is running all well, and suddenly you lost the connection. How can you ensure that your server process isn't really affected by this? Meaning that you try to establish a connection once again, instead of just terminating the process. So that's one challenge. Then you have another challenge, and that is creating a type-safe wrapper for your SQL statements. So for example, getting the to-dos, this could fail. Inserting a to-do, you might get a unique violation. Maybe title is supposed to be unique. So perhaps you want to translate that error over to a 400. And then you have the update to-do. Same thing, you can have a collision here, or maybe you want to map nullability over to a no such element error, etc. And finally, you have another challenge, and that is transactions. So let's say you want to access the context of the request here, or the context of the current user that your middleware provides. Or maybe you want to throw an error. So for example, you first check if an entity exists. If it exists, you could throw a new error and say conflict. Now you would use effect for all of this, of course, but as you can see, since Drizzle uses a callback style API, it is way more tedious. Now this depends on the client you're using. Some expose a db.start transaction, and then you can do your statements here, and then finally you can commit the transaction, but not all ORM support this. So let me show you how I solve all of these challenges. Now what I'm going to show you isn't particularly the right way to do it. It is simply the way I found out how to do it. But I'm pretty sure there are hundreds of different ways to do it. So first and foremost, I created a custom error, a tagged error at that, called database error. And here I just have a type for unique violation, foreign key violation, connection error, and well, you can add any other types that are missing here and that you need, of course. And then I stored the cause to have the original error, which comes from Postgres, because that's the dialect I'm using. So obviously this depends on your dialect. I then have a function, match PG error, which is going to take in error, which is of type unknown. And then I'm going to check if it is instance of pg.database error. If so, I switch upon the error codes and then match them over to the type. And if it doesn't match, I'm going to return null. And we'll see how I use this in a moment. And then I have another type of error, and that is database connection lost error, which in reality, I guess this could be called database init connection error. And this error is only used for when we try to establish a connection to the database. This is not for when we make queries. And then I have a make service, which takes in the URL, which is redacted because this contains the password and whatnot, and then SSL. Now, the reason why I have a make service is because this is a shared package. So all of this is in a PNPM monorepo. So that's why I accept the URL here instead of constructing it with my environment variables, because again, each service might have different environment variables. And here, what I do is create a scoped effect. So I create the pool and I do an acquire release. So this is the acquire creating the pool, and when releasing it, we're going to simply call pool.end. And this is going to add a scope to the requirements channel. So when the scope is closed, it is going to call pool.end. That way we have a nice declarative way to manage resources, which are ultimately managed by the runtime. Then I do a try promise to simply do a select one. And this is our confirmation to whether we have established a connection or not. So I just do a try promise so that we can have an actionable error. And upon this actionable error, I apply a retry policy. So jittered with 1.25 seconds, I specify the min max, and then just for observability in that sense, I added a log warning. So connection to the database failed, retrying with the attempt. That way we can check the logs just in case. And then once this is successful, we simply say connection to the database established. And then I have a setup connection listeners. And what I do here is simply listen for an error from the pool, because I noticed that if you shut down your database, for example, your whole process is going to crash. It is going to terminate with a defect. And this ends up being outside of effects control. So that meant that me running the server using effects runtime, particularly the bond runtime or the node runtime, if I shut down my database process, it crashed the whole process. So it killed my server. So for that, I need to listen for this error event and tap it into effect. So for that, I use async, and then when I get an error, I simply fail with a new database connection lost error. And actually, I set back what I said. This is not a database init connection lost error, but a database connection lost error. So the name is correct. And then here we can return an effect. And if I come here, as we can see, can return an optional effect that will be run if the fiber executing this effect is interrupted. This can be useful in scenarios where you need to handle resource cleanup if the operation is interrupted. So here we just remove all listeners, particularly for the error channel. And then I simply log database connection error listeners initialized. And this is all run concurrently, because if I do not set this concurrent to true, then this log will never be called. Then I created the database Drizzle client instance. So I pass in the pool, and then I pass in my database schema for the TypeScript types. And here's where the fun begins. So I created a wrapper around the client so that we can map the errors and do it all in an effectful way. So for that, I simply have an execute computation that is a function that takes in a callback, and this callback will give you the client. So this is what you can actually use to make the queries. And this returns a promise logically, because this is not in effect. And for this, I simply say try promise, and then I apply the function, pass in the database client, and then we catch the errors, match the PG error, remap it over to a database error, return that, and if we didn't match the error, then we're going to throw the original cause. And this right here is going to cause a defect. Makes sense. If we cannot match the error, then it is a non-typed error, hence it is not actionable. That means we're not handling the case, or well, this threw another error. So we're simply going to cause a defect on that. So this one is pretty simple. But what about transactions? We need to get access to the runtime, and we need to map the errors and be able to do it all in effect. So for that, same thing, an effect.function, and here we take in the execute, which is a callback, where you get access to the transaction client. And here you can invoke it, where you get access to the transaction client, and you can do your queries. And this is going to return an effect that is going to succeed with you, and it is going to fail with database error, logically. And so here what we can do is say effect.runtime. And this is going to access the runtime so that you can unsafely execute tasks. So here we say, okay, the type of the runtime will be R, because we assume that the context you are going to be using in the transaction is the context of ultimately your composed live layer. So everything is correctly tracked in the type system. And so this R is going to be propagated over to the parent, to the consumer. So if the consumer accesses something that isn't provided, then effect will let you know at compilation. And then here we pipe through this, we get access to the runtime, and then we can get the run promise exit function. And as you can see here, we get the run promise exit, your usual effect.run promise exit, but this one is bound or tied to the runtime. And then here we do an asynchronous effect. So effect.async, this is going to succeed with T, which is ultimately what your transaction will return. It is going to fail with database error, or E, because again, we're now providing an effectful way to interact with a transaction. So logically, we can propagate errors from there. And then we have the runtime, of course, or the context type. And then here we create a wrapper for the transaction client itself. So same thing as the other one, we wrap this up in a try promise, we apply the function, we pass in that transaction client, and then on any error, we're going to remap that over to PG error. And for this, we can simply say const result is equal to await run promise exit. So we're using the runtime's run promise exit, and we pass in the execute, which is what the consumer is going to pass in to run the transaction, and then we pass in our transaction wrapper. And then here we can match on the exit. So on success, we're going to resume with an effect.succeed value, which is of type T, as you can see here. So ultimately what the transaction will succeed with. And then we have the on failure, where we get access to the cause, we check if it is a failure, and if so, we fail with the original error. So any expected error or actionable error your transaction can fail with. And if it isn't a failure, so it could be an interruption or a defect, then we're going to die. So we're going to propagate that defect again. And then after all of this, I do a catch for the whole transaction. So the db.transaction, and we match the error. If it is a PG error, then we're going to fail with that. Otherwise, we're going to cause a defect. Now, I'm not entirely sure when this case would run, particularly because we're protecting the whole transaction with a run promise exit. But I guess the whole transaction computation can fail if there is no connection to the database or something along those lines. So that's why I added this catch here. And that's it. With this, we can now have effectful transactions. And I also created a utility called make query. So let's say you have repositories. So a to-do repository. And well, as you know, a repository can have multiple consumers under different contexts. So some might use an insert computation within a transaction, while others will not use a transaction whatsoever. So imagine how tedious it could become in your repositories to support both APIs. So for that, I have this wrapper that is going to give you the execute, which is going to be either the client or the transaction client. And then you can define your input. So what your actual computation will take in. And then it is going to return a function that is going to take in the input as the first argument. So as you can see, matches what you define. And for the second argument, the actual transaction. And then here we can do return query function, and then we pass in the transaction if it exists, and if it doesn't, then just execute, which again is our simple effect.try promise wrapper. And we pass in the input. That way you can easily support both contexts. And that's it. And with that, I expose everything, and then I export an effect.tag for the database, and also a layer function where we take in the config, and we basically do a layer.scoped database, so the tag, and what it will hold is make service, and we pass in config, and that's it. Great, so with this, let's now take a look at how to initialize this database service. So for that, if I come here to my server file, I have this database live. And what we do here is do a layer.unwrap effect. And as the name suggests, it is basically going to convert an effect into a layer. So it is going to take the success, the error, and the requirement channels and convert them into a layer. So if I come here, as we can see, takes in an effect that must succeed with a layer and can fail with E and requires R, and so it is going to succeed with a layer that is going to lift this A. So it is going to remove the E1 and R1 and move them over to the error channel of the layer and the requirements channel of the layer. That way we can access effects and convert them over to layers. So with this, we can say envars.pipe, and then we can map over the environment variables, we get them here, and then we can construct the database layer. So as you can see here, we can configure the URL, SSL, etc. And what we get back is a layer that succeeds with database and fails with config error. Why config error? Well, that's because envars fails with a config error because we're using the config module to validate the environment variables. And that's all we need to do. So with this, we can just provide it here, database live. However, we need to set up the connection listeners so that again, we can hook the pull errors into effect. That way, we can prevent the process from dying. So here we say layer.merge. Now, why merge and not provide? Well, that's because merge is going to do it concurrently. And this is very important because if you do not do a layer.merge but instead of provide, the setup connection listeners will only execute when we get an error from the pool. That means that it is going to run indefinitely. So none of these would run and hence your server would never start. So we say merge for that concurrent execution and then we can do a layer.effect discard. So constructs a layer from the specified effect discarding its output. And then we simply say .use and then set up connection listeners and that's it. And with this, if we come here and come over to server and then run this, we get an error because this is in use. But if I kill the process in use and run this again, as we can see, we get connection to the database established and the error listeners are initialized. Now, if I open up Docker and if I were to stop the database process, so stop, as you can see, the server crashed, but we still get retries. So as you can see, connection to the database failed, retrying. And if I run it up again, as you can see, connection to the database established, and we get the other log as well. And all of this is done here. So we catch all cause, and then we refail over to an unknown exception, just so we have an actionable error, and we can apply the retry policy to that, unless the error is a config error, because well, we know that no matter how many times we retry, the environment variables won't magically fix themselves. And that's it. As we can see, we do this jittered space to retry, and then we simply log a warning, just so we know what's going on. And with that, you're good to go. Okay, now to the fun part, using the database client. So for that, I created a test file. This is just for demonstration purposes. So here we have a test DB, we create the layer so that we can provide it for our test cases. And then here, what I recommend is creating repositories. So you always want to encapsulate the data access layer into repositories, so everything is more controlled and you have a defined source of truth. So for example, imagine this was a user's repository. So in that service, you would yield the database and then you would say db.makeQuery. So notice how I'm using this utility helper so that we can support transactions. And then here we get the execute, which as you know, gives us the client or the transaction client. And then here we can define the input for this computation. So here we can say execute, we get the client, we can do an insert, whatever you want here. And ultimately, this is an effect. You can map over it, you can filter, you can do whatever you want. And so that's the idea. In your repository, you would mostly have this db.makeQuery, you would add some spans and whatnot. And then in your actual consumers, you would yield this repository service. And then as you can see, the usage is very simple. Simply insert user, you pass in the arguments that correspond to this one right here, so username, and you can optionally pass in the transaction. As you can see, marked as optional if you do not provide one or just using the base client. And with this, as you can see, we can map over it, we can filter, and if I come here and do a catch tag, as you can see, we get the database error. So really nice, very basic. Now moving on to unique constraint violations, just to ensure that we're mapping over the correct error. So here we have again the insert user and the delete user. And what we do is insert a unique user and then we do it again. And we know that this should fail. So here, as you can see, we expect the error to be instance of database error and the type to be unique violation. And if I open up the output, as you can see, should handle unique constraint violations. So this is really nice because again, if you're using this at your controller layer, you can simply pipe over this, do a catch tag, get the database error here, and then actually change this to catch if. You can say if the error dot tag is equal to database error, assuming you have more than one error. And then you can say and the error dot type is equal to unique violation. If so, you can fail with a constant for new conflict. And now you mapped this error over to 409, I believe. And that's it. Now what about transactions? Well, as you can see, all you need to do is say db.transaction. You get back the transaction client here, or rather the callback. And as you can see, you can return an effect here. And that's the idea, so that you can get access to your context, so that you can remap errors here, so you can validate things here with the schema, well, so that you can leverage the power of effect. So here, as you can see, we yield the transaction wrapper, we get back the client, same thing as the other execute, and then we can do the inserts, and that's pretty much it. Now for a better example, as you can see, should handle transactions with rollback on error. So we have the count users computation, and then we can do a transaction, we insert a user, and we insert a duplicate user, and this should get rolled back because this failed right here. So we expect the count of the users to be 0. And as you can see, this passes. And well, of course, result is an either of either void or database error. So in fact, we could also assert that result is of type database error, or instance of rather, and that the error type is a unique violation error. And finally, we have nested transactions. So this also works. We have this outer transaction and this inner transaction, and everything works as expected. And that's it. So whether you're using Drizzle, you're using Prisma, whatever ORM you're using, make sure to expose an API where you can support transactions. So in this case, if I scroll up and do a const insert user, and then here we can yield insert user, and then we need to pass in the transaction. Same here, save this. Everything still works, so make sure to support that API for your repositories. Makes things more ergonomic. And also create wrappers for transactions so that you can support effects. which is what I've seen many people struggle with. The only thing that I did find hacky, and I'm not sure if this is the idiomatic way to handle it, and that is the retries, or setting up the connection listeners. So this right here, doing a layer.merge with an effect discard, having to do this manually feels a little bit hacky. I'm not sure if this is the way to do it, but hey, it works. And in fact, I've been using this setup for 3 months in production now, and I've had no problems with it. Anyway, this wraps up the video. You can find the repository in the description, and if you want to see more content like this, make sure to subscribe. I'll see you in the next one. See ya.